Okay. Magnetism. Today, we need to quickly revise magnetism and electromagnetic induction and DC motors, effects of the current on the wires. Okay, if we start off with magnetism, we know that we have a magnet with magnetic poles, north poles and south poles. Okay, any magnet would have a north pole and a south pole. Okay, and we can draw the direction of the magnetic field. The direction of the magnetic field will be from the north pole to the south pole. Okay, we draw the arrows moving from the north pole to the south pole. It's moving outside from the north pole and inwards into the south pole. Okay, and then we said, how can we find the direction of this magnetic field? Or, in other terms, what is the direction of the magnetic field? Okay, there's a question in paper 4, usually, sometimes in paper 2 as well. What is, I'll define the direction, okay? The direction of a magnetic field. Magnetic field. What is the direction of a magnetic field? Basically, it's the direction of the force. Okay, let's write it down. It's the direction of the force, of the force on a north pole. Okay, on north pole of a magnet inside the field. Inside the field. What does this mean? Direction of the force on a north pole inside this magnetic field. Basically, if we have a compass, if you have a compass, okay, what's a compass? Okay, compass is usually it has a north pole and a south pole. Compass is a very small magnet which can rotate, okay, which can be easily affected by other magnetic fields around it. So this compass has a north pole and a south pole, which could be easily affected if we put this compass inside this magnetic field. If you put the compass near, let's say, the north pole, if you put the compass near the north pole, it would be affected by the north pole. In which direction would it look? It would look to the right. Why would it look to the right? Because this is the north pole and this is the south pole. So basically, the south pole is attracted to the north pole. So the force on the north pole is to the right. The force on the north pole is to the right, and that's why we drew the arrow to the right. Again, if you draw another compass on this side, it would look also this way. Why? Because the north pole is attracted to the south pole. Again, the direction of the force on the north pole is to the right. So basically, what is the direction of a magnetic field? It's the direction of a force, okay, of the force on a north pole of another magnet in this field. If we have a compass here, it would look, how would it look? It would look to the left. So direction would be to the left. Why? Because the north pole is attracted to the south pole, okay, and the south pole is attracted to the north pole. Basically, direction as well is to the left. So this is the direction of the magnetic field, okay. um what are the magnetic materials we usually talk about? We usually talk about iron or steel. We have other magnetic materials such as cobalt and nickel. We have cobalt and nickel, but basically we talk about either iron or steel. And the difference between iron and steel is that iron is a temporary magnet. Iron is a temporary magnet, while the steel, okay, steel is a let's say that it's a permanent magnet. Okay, permanent, okay, anyway, magnet, meaning that it would keep its magnetism. The iron would instantly lose its magnetism. Iron will never remain a magnet for a very long time. Iron, we can use it in an electromagnet. What is an electromagnet? Basically, we need some circuit to create this electromagnet. We need a circuit to create this electromagnet. Okay, so if we talk about electromagnetism, one of the properties of any metal, okay, especially we talk about copper, okay, one of the properties of copper is that when you pass a current through the copper, it creates a magnetic field around it. when you pass a current through the copper, it creates a magnetic field around it. In which way? Okay, if I have a wire, okay, okay, this is sort of a 3D representation of the wire, okay, and you have the current passing in this direction. This is the current, okay, this is the current passing in this direction. For example, the wire is attached, okay, it's connected to a battery, okay, the battery has current in this way, so the current is moving towards the right in this copper wire. It will create a magnetic field around it, in which direction, using the right hand rule grip, right hand rule grip, using the right hand rule grip, in which you have your thumb, which is the direction of the current. The direction of the current is to the right. Therefore, if you close your grip, okay, if you close your grip, then the direction of the magnetic field would be somewhat in this direction. Okay, circular around. It's a circular magnetic field around the, okay, around the wire, around the wire. So it's a circular magnetic field around the wire. Usually, um, he would ask you to find the direction, but not in this way. This is more of a 3D representation. This is more of a 3D representation. Usually it would be more of a 2D representation. How so? He would tell you that the magnetic field is either into the page or out of the page. Into the page or out of the page. Okay, so into the page, into the page, or out of the page. Into the page, he would draw a very small X, indicating that the current is into the page. Out of the page is a very small dot, indicating that the current is moving outside or towards you, outside of the page. Into the page, using right hand rule grip, the right hand rule grip, you'd find that the thumb is moving into the page, and the remaining fingers are rotating in a clockwise manner. So the direction of the magnetic field would be clockwise. How can I draw the magnetic field around this point? Okay, you'd usually draw two circles using the compass, definitely using a compass. Okay, two very close circles, and then another one which is a bit further away. Okay, another one which is a bit further away. Why so? Because this tells me, as an examiner, that you know that as you get closer to the wire, you're closer to the wire, the magnetic field is much stronger. As you move away from the wire, the magnetic field gets much weaker. The more lines you have, the more lines you draw, this indicates that the magnetic field is much stronger. The further away the lines are, okay, the weaker the magnetic field. Basically, again, here on this one, we will draw two circles which are a bit closer, okay, and they're rotating in the opposite direction. Why? Because it's out of the page, the thumb is moving outwards. So if you close your hands, then the direction would be in the anti-clockwise motion, or anti-clockwise moment. Okay, and then you have another circle. Definitely, this is not a circle. You should use your compass. Okay, you should use your compass. Would you lose marks if you do not use your compass? Yes, you will lose marks if you don't use your compass. Okay, you have to draw two very close circles and then a further one. This is the direction of the magnetic field if you have into the page, or the current is moving out of the page. Okay, into and out. So basically, we kind of created a very small electromagnet. Why is it called an electromagnet? Because once you switch off the circuit, once I switch off this battery, what will happen? The magnetic field will go away. Okay, it won't remain in the wire. It's not constant magnetic field. Okay, magnetic field won't be there anymore. Okay, and this is if I have a straight wire. This is if you have a straight wire. What happens if you have a coil or a solenoid? What happens if I have a coil or a solenoid? A coil or a solenoid. Coil or a solenoid, basically a wire, but I rotated this wire uh, around, for example, an iron bar, okay, around an iron bar. So this wire would look somewhat like this, okay? this wire would look somewhat like this. Okay, so this is the coil or the solenoid, which is connected to a battery. Again, it is connected to a battery. The direction of the magnetic field inside this coil, direction of the magnetic field inside the coil would be straight lines. Inside the coil would be straight lines. Okay, straight lines, whether it's from north to south or south to north. And outside the coil, it would be somewhat like a magnet, like a bar magnet. Outside the coil, it would be like a bar magnet type. I guess this is pretty easy. Inside the coil, straight lines. Outside the coils, curving like a bar magnet. The question or the more difficult part is, where is the North Pole and where is the South Pole? That's the more difficult part. Where is the North Pole and where is the South Pole? And honestly, you don't have that many questions in paper 4 or paper 2 asking you about the direction of the magnetic field in a solenoid. You don't have that many questions. But for the sake of, if you ever encounter one of these questions, okay, you need to know how to find the direction of the magnetic field inside this coil. How can I find it? Using the right hand rule grip again. Using the right hand rule grip again. It's a bit tricky, but let's try it out. Okay, it's a bit tricky, but let's try it out. I will try it out, but I just need to state some facts about this coil or about this electromagnet. Okay, let's write down, for example, some of the advantages of using an electromagnet. Okay, some of the advantages of an electromagnet. Why would I use an electromagnet rather than a bar magnet? A permanent magnet. Why would I use an electromagnet rather than a bar magnet? First of all, okay, you can switch it on and off. You can switch it on, okay, and off. While on the other hand, the bar magnet is always on. The bar magnet always has a magnetic field around it. So this is one of the advantages of an electromagnet. You can also say that the strength of the magnetic field can be varied. Okay, you can control the strength. How can I control the strength? Okay, I actually have three other points which we need to discuss. Okay, how to control the strength of this electromagnet. You can control the strength of this electromagnet. And third, but last but not least, we can switch the polarities. Okay, we can switch the polarities, meaning that I can switch the north and south poles. How can I switch the north and south poles? By switching the direction, by switching what? The direction of the current. If you switch the direction of the current, if you reverse the direction of the current, then you have reversed the magnetic field. You have reversed the north and south poles. How can I control the strength of this electromagnet? Okay. How can I control, okay, controlling the strength of the electromagnet? First of all, you can increase or decrease the current. Okay, so the current affects the magnetic field. It's directly proportional. As you increase the current, the magnetic field increases. As you decrease the current, the magnetic field decreases. So by changing the current, you can also increase or decrease the number of turns in the coil. Okay, number the number of turns in the coil. If you have too many turns, then the strength of the magnetic field will increase. If you have much less turns, then the strength would definitely decrease. So the number of turns affects the strength of the magnetic field. Again, it's also directly proportional. And the third point is by adding a an iron core. By adding an iron core. How can you add the iron core? Okay, basically you have the iron core. It has to be an iron core. Okay, and then you just have the coil or the solenoid moving around this iron core. Can I use a steel core? No, you cannot use a steel core. Why? Because if you use the steel core, it would be magnetized. It would be a permanent magnet. So basically, you cannot switch off the magnetic field. You wouldn't be able to reverse the magnetic field. Sometimes you wouldn't be able to control the strength. Okay, so you must use an iron core. You must use an iron core. Why? Because it's a temporary magnet. Basically, when you switch off the current, it would instantly be switched off. The magnetic field would instantly be switched off. You can also reverse the direction of the magnetic field whenever you want. You can do whatever you like with this iron bar. And the question, again, moving back to the question, how can I find the direction of the magnetic field if I have this iron core? If I have this iron core, you need to understand, or you need to actually look at it quite carefully. You need to look at it quite carefully. Is the coil rotating above or below the um, bar? What do you mean? What do I mean by is it rotating above or below the bar? Okay, so this is my iron core. This is my iron core. Okay, above or below the bar, meaning the first, okay, the first coil. I'm talking about the only first part of the coil, the first part of this wire. Is it moving above or below the core? For example, if it's moving this way, then it's moving above the coil, okay, and then it would rotate all the way from the back, and then come from here, and then go back, okay, to rotate from the back and come. Okay, so I'm talking about the first point of the first point of this coil, the first point of this coil, okay, and then you have the it's attached to a battery, okay, and then the remainder of the coil, okay. So I'm asking about the first point. From this point of view, okay, from this point of view, if you go along with the current, this is the direction of the current. This is the first point, the first part of this wire, which is moving above. It's moving above the core. So using your right hand rule grip, using your right hand rule grip, you'd say, oh, this is moving from above the core. It's moving from above the core, and the current is moving this way, kind of moving to the right. Okay, sorry, kind of moving to the left. So the magnetic field would be north and south. The North Pole would be on the right hand side, and the South Pole would, I'm sorry, North Pole would be on the left hand side, and the South Pole would be on the right hand side. I don't understand. What do you mean? Let me draw another one. Let me draw another drawing. Or actually, I'll open up some questions so that you can see the drawings a bit more accurately. Okay. Again, this is the iron core. Okay, this is the iron core, and you have the current. Okay, you have the current which is moving again in the same direction. You have the current moving in the same direction. How's the current moving in the same direction? This is battery, okay? And then if you look at the wire, the first part of the coil, it's actually moving from behind it, okay? And then it keeps on moving, it keeps on rotating or moving around the iron core. I'm asking about the first part, Shab, the first part of this coil. Is it moving above or below the iron core? If it's moving above the core, it's like the first drawing. If it's moving below the core, it's like this drawing in which the coil kind of moves below below the iron bar or below this core. So if you have your right hand rule grip, then the North Pole would be on the North Pole would be on the right hand side, and the South Pole would be on the left hand side. طب I still do not understand, and I can't see anything from your drawings. Can you show us more questions from our classified questions? Yes, I can. Okay, let me open up a couple of questions from paper 2. Okay, let me open up a couple of questions from paper 2. 1 second, let's open up paper 2, classified questions in the magnetism. Okay, I'll tell you exactly page what question. Um, okay, okay. So you have magnetism, which is on page 186. If you open up, for example, question. Hmm. Okay, let's check out this question. Okay, let's check out question 8, which is on page 190. Okay, question 8, which is on page 190. I know this question he doesn't want, this question he doesn't actually want the direction of the magnetic field. But for this question, what's happening? You have an electromagnet on the left-hand side. Can I find the direction of the magnetic field of this magnet? Yes, I can find the direction of this magnetic field. How so? Because the current would be moving in this direction, okay? The current would be moving in, okay, in this direction. So, and then the first part, okay, if you check it out, the first part of the coil is moving above. The first part of the coil is moving what? Above the coil, so above the core, above the core. So if you use your Fleming, if you use your right hand rule grip, if you use your right hand rule grip, then the thumb is pointing towards the left. The thumb is pointing towards the left, and therefore the left part would be a north pole, and the right part would be a south pole. Okay, I know this is not the question. He does not care about what's happening in which direction is the magnetic field for this question. Okay, I know he doesn't care about that, but I'm telling you, for this question, you'd have a north pole on the left-hand side and the south pole on the right-hand side. Actually, the answer for this question would be if the switch is closed, the electromagnet magnetizes quickly. What happens to the reading on the voltmeter? This magnetic field, okay, would basically cut the other coil, causing an induced current, which increases the voltage, increases the reading on the voltmeter, but then it decreases to zero. Okay, it goes back to zero. Why does it go back to zero? Because it needs to constantly keep on changing, constantly keep on moving. Electromagnetic induction, we will discuss it later on, inshallah. But as for this question, the north pole is on the left hand side, the south pole is on the right hand side. Okay, this is another interesting question. You have, he's asking, in which direction will these magnets move? Will one of them move to the left, one of them move to the right? Will they both attract? Will they both be repelled? I have no idea. Again, using your right hand rule grip, using your right hand rule grip. The first, let's check out the current. The current is moving this way. So the first part of the coil, the first part of the solenoid, is it moving below or above? Is it moving below or above? Well, it's moving below. So it's moving below this core. So using your right hand rule grip, you'd find that the thumb is pointing towards the right. The thumb is pointing towards the right. And so this is the North Pole and this is the South Pole. Basically, this bar will repel and this bar will also repel. So both of them are repelled by the coil. They are both repelled by the coil. Again, using what? Using a right hand rule grip. I know it's a bit confusing. It might be a bit confusing at first, but again, that's what I'm here for. Okay, to try to help you with this sort of confusion that you have. Okay, I guess we have other questions. Yes, two circuits are set up. Okay, what happens to the size of the gap at X when switch S is closed? Size of the gap at S when switch S is closed. طيب. For this question again, can I use the Fleming's left hand rule? Sorry, the right hand rule grip. Can I use the right hand rule grip? Yes, definitely I can use the right hand rule grip. Okay. For the first part of the question, you'd find that the current is moving in which direction? It's moving in this direction. So it's moving in this direction. طيب. Using right hand rule grip, you'd find it's moving above the coil. It's moving above the coil. So as it moves above the coil, I need you to imagine that you're holding the coil. Okay, I need you to imagine that you're holding this core. As it moves above the core, as it moves above the core, you'd find that the north pole is on the right hand side and the south pole is on the left hand side. So North Pole is on the right hand side and the left pole is on the left hand side. طيب. What about the other one? Okay, what about the other one? The current is moving above or below. لا, this is moving below. So kind of if you hold the core using your right hand, okay, if you hold the core using your right hand, you'd find that the thumb is pointing towards the left hand side, and therefore the North Pole is on the left hand side and the South Pole is on the right hand side. North and North, what will happen? They would repel. They would repel. So basically, the size of this gap, what would happen to the size of this gap? It would increase. It would definitely increase. So that's how we can find the direction of the magnetic field using a coil, using a solenoid. Okay, basically, if your right hand, or if the first part, okay, the question is the first part of this coil, is it moving above or below? Is it moving above or below this core? Okay, you can then find the magnetic field. I know this question again. He's not asking this question again. He's not asking about the direction of the magnetic field. But can I find the direction of the magnetic field? Yes, I can. Okay. Yes, I can find the direction. Again, the current is moving in this direction. This is the current moving in this direction. So basically, the first part of the coil is moving below the core. صح? It's moving below the core. So using your right hand rule grip, okay, I'm kind of holding the core. I'd find that the thumb is pointing in this direction. So this would be the North Pole and this would be the South Pole. So this would be the North Pole and this would be the South Pole. What happens when the current is halved? Again, we said that the magnetic field in the electromagnet is affected by the current. As you increase the current, the magnetic field is stronger. As you decrease the current, the magnetic field gets weaker. So some pins are attracted, but not as many. Not as many. Why? Because as you decrease the current, the magnetic field would decrease. Okay. Um, so yeah, basically these are some of the more difficult questions we have in paper two when I'm talking about magnetism. This is a really interesting question. Okay, question 18. This is an interesting question. Wire P carries a current directed perpendicularly into the page. So using your right hand rule grip, can I find the magnetic field? Yes, I can find the magnetic field. Okay, into the page, it would rotate in a clockwise manner. So it would rotate in a clockwise manner. So it's moving basically in this direction. So basically it's moving in this direction. Now, clockwise, moving in this direction. Can I find can I find the direction of the force on the North Pole at point Q? At point Q, can I find the direction of North Pole? Yes. How can I find it? It's in this direction. How is it in this direction? So do I mean that the answer is A? Yes, the answer is A. Why? Because if I have a magnet, uh, um, if I have a compass at this point, the compass would be pointing in this direction. Now, if I had a compass at this point, it would be pointing in this direction. What about in this point? It would be pointing in this direction. At this point, it would be pointing in this direction. So basically, he's asking about the direction of the magnetic field in that point. Oh, at the point. Okay? It would be A. Another interesting question. This is an easy question actually. Which statement is the direction of the center? Okay, direction of the magnetic field at the center of this solenoid. The center of the solenoid, I said, they have to be in straight lines. Straight lines. So they have to be parallel to the axis. Parallel to the axis. Parallel to the axis. Okay, parallel to the axis. Okay. And actually, if you think about it, you'd find that the first point, the first part of this coil is moving above the core. Do I have a core? No, you don't have the core. But if you imagine that you had a core, if you had a core in this solenoid, the first part of this solenoid would be moving above the core, rotating above the coil. And this is the current moving in this direction. So if you move above the core, and then you have the thumb pointing towards the left hand side. So this is the North Pole and this is the South Pole. Okay, North and South. I'm trying to find more difficult questions actually. These are very easy questions. All of these are quite easy questions. Again, see, for this question, the current is moving in which direction? It's moving in this direction. And you have the core in the middle. You have the core in the middle. if you use your right hand rule grip, you'd find that the thumb is pointing towards the right. And that's why this is the North Pole. North Pole is moving out of the magnet. So it's moving outside, and this is the South Pole. The direction is moving into the South Pole. Okay? It's directed inwards. Actually, this question he's asking about the strongest magnetic field would be at sea. He's not asking about the direction, but I'm telling you how can you find this direction. Okay, this is actually the hardest part in magnetism. Literally, the hardest part of magnetism is finding the direction of the magnetic field in a solenoid. Okay, again, in which direction would the compass needle point? Compass needle would point to the right. So North Pole would point to the right. These are all quite easy questions. This is actually electromagnetic induction. Okay, to induce current, you need to use a magnetized steel rod. You need to use a magnet, basically. You need to use a magnet, north and south pole. These are all rather easy questions. Okay, I don't think we have any more very difficult questions. Okay, magnetism is not that difficult for for O-level students. Okay, not that difficult. For example, this question, I know it's easy, but we can solve it. Okay, the field. Which of these fields is stronger? The stronger field would be the first field. Why? Because the lines are closer together. So this is the stronger field. Field one, the larger force. In which direction, okay, is the electron? I know this is misplaced. This question is misplaced. It's not actually magnetism. Okay, this is more of charging. The electron, in which direction would this electron move if you had this would be the negative part, and this would be the positive part of the field. If you have an electron, then the electron would move downwards. Why would the electron move downwards? Because it's attracted to the positive side of the field. Okay, so the answer would be A. Okay, again, I'm trying to find more difficult questions, but honestly, they're all quite easy, rather easy questions. Okay. Um, I mean, this is again an easy question. Okay, this is a really easy question. In which direction would the magnetic field be? Okay, this is into the page. If you rotate, okay, into the page, it's moving in a clockwise manner. Clockwise manner type. Would it be A or would it be C? I think it would be C. Why would it be C? Because as you move away from the magnetic, as you move away from the coil, as you move away from the coil, the magnetic field gets weaker. A is wrong. Why? Because the you can't say that the magnetic field is equal at any distance from the magnet, at any distance from the wire. Okay, as you move away, the magnetic field gets weaker. It has to get weaker. Okay, so that's why it is C. Okay, I guess this is all I need to say about the magnetism. This is all I need to say about the magnetism. This is probably the last question I want to solve. You have the soft iron rod from the core, and you have um, the battery. In which direction is the current moving? The current is moving in this direction. It's moving in this direction. Can I draw the magnetic field? Yes, I can draw the magnetic field. The first part, okay, the first part of the coil, the first part of the coil, it's moving above the first part of the coil, it's moving above the iron rod. Only the first part. I'm asking about the first part of the coil. It's moving above. So using your right hand rule grip, using your right hand rule grip, it would be moving in which direction? You'd find the thumb pointing towards the left, and the okay, so the north pole is on the left side and the south pole is on the right side. Okay, can I draw the magnetic field? Yes, I can draw the magnetic field. It's moving from the north pole to the south pole. So the answer would be if I have a compass at point P, if I have a compass at point P, it would be directed towards the right of the page. Okay, towards the right of the page using your right hand rule grip. Okay. Moving on to the next part of today's session, the more, I don't want to say the more difficult part, Sometimes you find it a bit more intricate, but it's not that difficult. Okay. I want to talk about DC motors and AC generators. I want to talk about the effects of this magnetism. Okay. If you have two magnetic fields, the effect of two magnetic fields, how can we create a DC motor, or how can I create an AC generator? So basically, if I start off with DC motors, I know it's DC motors. How can I draw a very simple DC motor? Basically, you need a north pole, okay, and a south pole of magnet. You need the north and the south pole of a magnet. And then you need a coil inside this magnet. Okay, you need a coil inside this magnetic field. This coil has to be attached to, okay, it has to be attached to a slip ring commutator. Something called a split ring, not a slip ring, split ring commutator. Split ring commutator. Okay, which is a very crucial point, a very crucial part of this DC motor. Split ring commutator and brushes, which are connected to, okay, you need to draw the brushes. Am I required to actually draw these draws a DC motor in the test? Sometimes very rare questions you might be required to draw this DC motor in very rare questions. Okay, in paper 4, for example. Okay, so now you have the battery, you have a split ring commutator. Okay, let's write it down. A split ring commutator. What does this split ring commutator do? It actually reverses the current every half rotation to keep the coil rotating in the same direction in a continuous rotation. In a continuous rotation. Okay, this is a split ring commutator. And then the brushes, what do the brushes do? They basically keep the split ring commutator and the wire in place. He will never ask you about the brushes, okay? But he will ask you about the split ring commutator. What does it do? It keeps the coil rotating in a continuous motion. How does it do that? By reversing the current every half rotation. Now we have a magnet, a permanent magnet. We have a permanent magnet, and direction of the current, direction of the magnetic field in this permanent magnet is from the North Pole, to the South Pole. From the North Pole to the South Pole. So this is the direction of the magnetic field. Is there another magnetic field? Yes, there is another magnetic field due to the current in the wire. So this is the other magnetic field, okay, which is moving in this direction. I'm moving back to um, the battery. You have a battery and you have um, a battery and you have a magnet. You have a coil, a current carrying coil. So we can call it a current carrying coil or a current carrying wire. Current carrying coil or a current carrying wire. Can I find the direction of rotation? Yes, I can find the direction of rotation using Fleming's left hand rule. Using Fleming's left hand rule. Using Fleming's left hand rule, you'd have the index finger, which is sometimes we call it the first finger, or the index finger. This is the direction of the magnetic field, direction of the magnetic field. So basically, my first finger or my index finger is pointing towards the right in this question. It's pointing towards the right because the North Pole, okay, the direction of the magnetic field is always from the North Pole to the South Pole. So the index finger is pointing towards the right. The middle finger, sometimes we call it the second finger, and I'll tell you why. The middle finger is the direction of the current. Direction of the current. Direction of the current on the left part of this coil, on the left part of this coil is moving downwards. The direction of the current on the right part of this current is moving upwards. On the left part, it's moving downwards. On the right part, it's moving upwards. Sometimes to actually memorize it, second finger, middle finger, second finger C with the current C. So current, second finger. Okay, if you want to memorize it, second finger, current. And then you have the thumb, which is the force on this wire. So let's Demonstrate. Let's try to demonstrate it on the left part of this coil. You have the direction of the magnetic field. It's moving from north to south, and then you have the direction of the force, which is moving downwards. Sorry, I'm talking the direction of the current, which is moving downwards. Then you have the direction of the force, which is moving out of the page. Direction of the force is moving out of the page. So if I ask you in which direction will this part of this coil move, okay? So using this color, let's use this, okay? This would move out of the page. What about this part? It would move into the page. It would move into the page. Again, why? Because using Fleming's left-hand rule, you have the magnetic field, it's moving towards the right, and the current is moving downwards. Therefore, the force on this part of the wire would move out of the page. If you flip your wrist, again, all you change is the direction of your wrist. Don't change anything. The three of these forces, or the three of these properties, have to be in 90 degrees. They have to be perpendicular to each other. They have to be perpendicular to each other. All you do is just rotate your wrist. So you have your north pole again to the right hand, or to the right side, but the current is moving upwards. So all you do is rotate your wrist. So you have your middle finger moving upwards, and therefore the thumb, which is the force, is moving into the page. The thumb is moving into the page. So the left hand side is moving out of the page, the right hand side is moving into the page. It will keep on rotating due to the split ring commutator, which allows this rotation. Why? Because it keeps on changing. Okay, sorry, it keeps on changing the reversing the current every half rotation to keep rotating in a continuous motion in the same direction. Continuous motion in the same direction. Okay, this is the split ring commutator. It's a crucial part of the DC motor. Without it, it would keep on rotating quarter rotation one direction, then a quarter rotation or half rotation one direction, then half rotation in the other direction, which is completely wrong. Okay, so this is a DC motor. Okay, this is a simple DC motor. Very simple DC motor. What does it do? It uses the chemical energy, or let's say uses the electrical energy in the wire, okay, to produce a kinetic energy, a motion, produces a motion. So electrical energy is changed, is transformed to kinetic energy. Electrical transformed to kinetic. Can I reverse this operation? Yes, I can reverse this operation using the AC generator. Using the AC generator. How do I know? Sometimes we call it electromagnetic induction. It doesn't have to be an AC generator. Sometimes we call it a electromagnetic induction. So how do I induce? What do I mean by induction? Okay, induction is basically producing or generating a current. Producing or generating a current. How can I induce this current? Let's write it down. This is an AC generator. AC generator. AC stands for alternating current. Stands for alternating current. So how can I produce this current? Basically, you need to move a wire inside the magnetic field. You need to move this wire inside this magnetic field. Okay, how can I move this wire inside the magnetic field? You can simply have let's draw it in a much simpler way. How can I draw it in a much simpler way? If I have this coil, okay, oh, actually, let me draw it in a 3D motion. Okay, let's draw it in a 3D representation. You have the North Pole, okay, let's draw a 3D magnet, okay, this is your 3D magnet. This is the North Pole, okay, and then you have a South Pole on this end, okay, this is the South Pole. And then the direction of the magnetic field, it's moving from the North Pole to the South Pole. This is the direction of the magnetic field, from the North Pole to the South Pole. Then we have a wire. You can bring a wire, okay, in the middle, attached to a galvanometer or an ammeter or a voltmeter or whatever. It's a meter that indicates that there is a current or there is a voltage in this wire. Okay, we can call it a galvanometer. Okay, galvanometer. You can call it a sensitive ammeter, a sensitive voltmeter, or whatever. What do I do with this galvanometer, or what do I do with this wire? Basically, if you have this wire and you start moving this wire, if I start moving the wire, then a magnetic field, okay, oh, this wire, let's say this wire will start to cut the magnetic field. This wire will start to cut the magnetic field. As it cuts the magnetic field, it produces a current. It induces a current. Okay, an electromagnetic a current is induced in the wire. An EMF is induced in the wire. An EMF is induced in this wire. In which direction? In which direction? It has to do with the direction of the motion. The motion has to be perpendicular to the magnetic field. It has to be perpendicular to the magnetic field. Perpendicular. Meaning that if I start to move this wire to the left and to the right, towards the North Pole and towards the South Pole, will a current be induced in this wire? No. It has to move either upwards or downwards. Why? Because it has to cut the magnetic field. Okay, so basically cutting the magnetic field is the main key word while talking about electromagnetic induction. Whenever you have electromagnetic induction, you have to state this word. You have to say it. Cutting. It cuts the magnetic field, not literally, not using the scissors, but kind of metaphorically, because it's passing through this, okay, passing through these magnetic field lines. So as the wire passes through the magnetic field lines, what happens? It cuts these magnetic field lines, producing an induced current, or inducing a current in the wire. Inducing a current in the wire. How do I know that the current is induced in the wire? If I check out the galvanometer, I would find that the galvanometer starts to deflect to the left or to the right. You'd find that the galvanometer will start to deflect to the left or to the right, indicating that there is a current or there is an EMF in this wire. Basically, because of the motion. It's caused because of the motion of this wire. If you move this wire up or down, if I move it to the left or to the right, you'd find that the galvanometer will not deflect. Okay, it will not move at all, indicating that there is no current in this wire. Okay, okay, so you have the wire moving up and down, cutting the magnetic field. Can I find the direction of the current induced in this wire? Yes, I can find the direction of the current induced in the wire using what? Using Fleming's right hand rule. Okay, Fleming's, okay, right hand rule. You can find the direction of the induced current. So if the question tells you there is an induced current in the wire, then you can use Fleming's right hand rule. If you find a galvanometer or an ammeter or a voltmeter in the question, then you would use Fleming's right hand rule. Why? Because you can find the direction of the magnetic field. The direction of the current in the wire. Okay, some keywords that indicate that this is an AC generator, that you are inducing current. Okay, for the previous question, for a DC motor, how can I make sure that I want to use or that I have to use the Fleming's left hand rule? If you find a battery, then you would use Fleming's left hand rule. If he says that this is a current carrying wire, a current carrying wire, then you would use Fleming's left hand rule. Okay, if he says he switches on a circuit, خلاص, this is a Fleming's left hand rule. But this is Fleming's right hand rule. Can I find it? Yes. Again, the index finger is the direction of the magnetic field, which is always from the North Pole to the South Pole. It's always from the North Pole to the South Pole. If I start to move this wire upwards, for example, if I start to move the wire upwards, this is the direction of the force on this wire. Okay, this is the direction of the force on Anna. I'm creating this force. I'm exerting this force on the wire. So due to this force being exerted on the wire, a current will be induced in the wire. How will this current be induced in the wire? Using Fleming's right hand rule, you'd have the North Pole to the South Pole, which is the direction of the magnetic field. Then the force is upwards. Using your right hand rule. Okay, again, the force is the thumb, and the middle finger is the direction of the current. The middle finger is the direction of the current. You'd find that the current is kind of moving into the page, or it's moving in this direction. If the force is upwards, then the current would be moving in this direction. So this is the current. It would move in this direction. If I move it upwards, if I move it downwards, okay, if you move it downwards, then the current would move in the opposite direction. would move in the opposite direction. Why do I call it an AC generator? Because usually it's not only one wire. It's usually a coil. Usually a coil. And you start to rotate this coil. Okay, you start to rotate the coil. So as one of the coils moves upwards, another one moves downwards, creating an alternating current. Creating an alternating current which moves in two directions. Moving in two directions. Can I demonstrate the electromagnetic induction using in another way? Yes, I can demonstrate it in another way using a coil or using a solenoid. Okay, I would um, uh, I would have a, let's say, an ammeter, a galvanometer. Okay, which is attached to a coil or a solenoid. Okay, and then you have the magnet. This is the magnet, North Pole and the South Pole. As the magnet moves, okay, as the magnet moves towards the left, what happens? Okay, the magnet has a magnetic field, okay, magnetic field north and south. Okay, this is the magnetic field north and south. As it moves, the magnetic field lines cut, magnetic field lines cut the coil, inducing an alternating or inducing a current in this coil, and therefore the ammeter will start to deflect. The other question, the more difficult question is, what is the direction of the magnetic field created by the coil due to the motion of this magnet? What? I have no idea. What have you said? Okay, now this magnet is moving towards the left. It's moving towards the left. And a current will be created inside this coil. Think about it this way. The magnet is moving towards the left, and the current will be created inside, or current will be induced inside this coil. Also, electromagnetic induction. So when you have this current inside this coil, when you have this current inside this coil, won't this current create a magnetic field? Yes, it will create a magnetic field. In which direction will this magnetic field be? Okay, it depends on two things. It depends on two things. On the polarity of the magnet and on the direction of the motion of this magnet. What do I mean? If this magnet is moving towards the left, let's say that the motion of this magnet is towards the left. The motion of this magnet is towards the left. Then the magnetic field created or the magnetic field induced in this coil would be North Pole on the right and the South Pole on the left. Why? Why? Let's draw another one. Let's draw another one, and I'll tell you why. Don't worry. I will tell you why. Okay. Let's draw another one. Okay. If I have a coil, okay, if I have an ammeter, okay, and the coil, and then you have a magnet, okay, with the North Pole, okay, from North Pole and South Pole, North Pole and the South Pole, and then you have the magnetic field around, okay, this is the magnetic field around the coil, the magnet, but this time the motion, okay, this is the motion of this magnet. The motion of this magnet was towards the, okay, the motion of this magnet was towards the right. Then this part of the coil would be a south pole, and this part of the coil would be a north pole. Okay, why is so? Why is that so? Because the current created in this coil, what does it do? It opposes, okay, it opposes the force, okay, it opposes the force that creates it. What do I mean by that? It opposes the force creating it. If we think back to Newton, if we think back to Newton, well, when Newton said that any force, okay, or any force, okay, has any action has an equal and opposite reaction. Any action has an equal and opposite reaction. Okay, we need to think about it quite thoroughly. Any action has an equal and opposite reaction. As the magnet is moving towards the coil, in the first example, as the magnet is moving towards the coil, what happens? The electrons inside the coil, and this is a coil, it's a good conductor of electricity, so the electrons inside the coil are kind of irritated, okay? They're moved. They don't want to move, okay? Initially, anything at rest tends to stay at rest, and anything in motion tends to stay in motion. Okay, so these electrons are sort of at rest. They're not at rest, I know, but they're sort of not moving. They're sort of not freely moving between the atoms at this instant. As the magnet moves towards them, what happens? They're kind of irritated. They're moved. They're pushed by this magnetic field. They are pushed by this magnetic field. So they want to fight back. They want to fight back. How can they fight back? By creating another force, by creating an opposing force, by creating what is an opposing force. So as you push the magnet inwards, it wants to create an opposing force outwards. It wants to create what is an opposing force outwards. So that's why if the magnet is moving towards the coil, what will happen? It will create an opposite. It will create an the same pole. It will create the same pole. Why would it create the same pole? To oppose the motion or to oppose the force acting on it, to oppose the force acting on it, because now it wants to oppose it, kind of, it wants to push it back. It won't push it back, I know, but it kind of wants to push it back. Okay, as the magnet is moving outwards, again it wants to oppose the motion. It wants to oppose the force acting on it. Now as it's moving outwards, it will create a magnetic field which is opposite, to pull it back. It wants to pull it back. It doesn't actually pull it back. It doesn't actually pull the magnet backwards, but it wants to. Okay, it's trying to react to the motion of this magnet. It's trying to react to the motion of this magnet. So it kind of wants to pull it backwards, but it cannot pull it backwards. So all it does is just create a magnetic field which opposes the motion of this magnet. It opposes the motion of this magnet. If I draw two other coils on this side, okay, if I have an ammeter, okay, which is okay attached to a coil, and another ammeter, okay, another ammeter which is attached to another coil, okay. If you think about it, this south pole is moving in which direction? It's moving towards the left. This south pole is moving towards the left. I'm talking about the right hand. Okay, so if it's moving towards the left, then this pole would be a north pole and this pole would be a south pole. Why? Because it wants to attract it, that it wants to oppose the motion. This pole, this south pole, is moving towards the right now. So this part would be a south pole and this part would be a north pole. Again, why? Because it opposes the force acting on it. It opposes the motion. Okay, it just wants to say, no, I don't like it. I want to stay in motion. That's Newton's law. Okay, Newton's law. Any action has an equal and opposite reaction. It's always the opposite reaction. Okay, it's creating an opposite magnetic field. An opposite magnetic field. Type. Okay, yes. This is actually the most, honestly, this is part of, kind of the most difficult part of this, of the electromagnetic induction. Okay, probably one of the more difficult parts of the electromagnetic induction. Can we solve some paper 4 questions? Yes, we can solve some paper 4 questions. So let's open up paper 4. Okay, let's open up paper 4. Okay, paper 4. In yalla, paper 4 part 2 definitely. Okay, okay, paper 4 part 2. Hmm. Okay, just opening up paper 4 part 2 on electromagnetic induction. Electromagnetic induction. Yes, 1 minute. Page, it should be page 353. Okay, 352, which is yeah, page 352. Okay, page 352 or page 450, both questions. Is this part of page 351? Yes, it is page. No, it's not part of page 351. Okay, yeah, page 200 and 352. Page 352. Okay, have you all opened it up? Okay. Hmm. Let's check out this question. Okay, this is an interesting question. It's an interesting question. Figure 8.2 is a voltage time graph showing the output of a simple alternating current AC generator um, at times T0, T1, T2, and T3. T0, T1, T2, and T3. Figure 8.3 is an end view of the plane of a coil, okay, of this generator at T0. At T0. Initially, AB initially AB was in this um, it was in this position at T0. Can I check out T0? Yes, T0, the voltage was what? The voltage at T0 was zero. Voltage at T0 was was zero. No voltage. So this is an output voltage of zero. Output voltage of zero. It's rotating in which direction? It's rotating in a clockwise manner. It's rotating in a clockwise manner. It's rotating in a clockwise manner. When, okay, this is a question, a nice question. When will this coil, okay, when will this coil complete a full rotation? When will it complete a full rotation? When it goes back to this same position, A and B. This means that it has completed a full rotation. 360 صح 360. This is a complete rotation when it goes back to A and B. Okay, this is actually a math question. It's not a physics question. It's more of a math question. Draw the end view of position at T1. Include the labels A and B. Include the labels A and B. At T1, okay, at T1, in which direction will this coil be rotated? It's rotating in a clockwise manner. طب how much of this rotation has it already completed at T1? At T1, how much of this rotation has it completed? If you think about it, okay, this is 90 degrees. This is only quarter of the rotation. This is only quarter of the rotation. At this point, okay, which is not stated yet, this point is 180 degrees. This point is 360. This point is 360. This point is 180. So at this point, it's 90 degrees, meaning that it has only completed 90. It has only completed 25%, only a quarter of the rotation. Only a quarter of the rotation. So initially it was vertically. At this position, it would be horizontally. At this position, it would be horizontally, and A would be on the right hand side and B would be on the left hand side because it's rotating in a clockwise manner. If it was rotating in an anti-clockwise manner, then A would be on the left hand side and B would be on the right hand side. Okay, so it's rotating in a clockwise manner. At T1, it has completed only a quarter of this rotation. Only a quarter of this rotation. Draw an end view of the position of the plane of the coil at time T2. At time T2. At time T2, has it completed a full rotation or not yet? At time T2, yes, it has completed a full rotation. T2, it has completed a full rotation. So at this point, it would go back to A being towards the top and B being towards the bottom. So at this point, it has completed a full rotation, and A would be here and B would be towards the bottom. Okay. Okay. Question triple I, draw an end view of the position at time T3. Time T3. At T2, I have completed a complete rotation at T2. At this point, again, another 90 degrees. Okay. At this point, another 180 degrees. At this point, another 270 degrees. Meaning that I have completed 3/4 of a rotation. 3/4 of a rotation. So this was initially AB. Okay. A quarter of a rotation would be AB. A half a rotation would be AB. This is half a rotation. But then 3/4 of a rotation would give you A on the left hand side and B on the right hand side. Okay, it's moving in a clockwise manner. A would be on the left hand side and B would be on the right hand side. Okay, A and B. I know it's a new question. It's a new question. We don't have that many questions asking about this. But again, that's what variant 3 is there for. That's what variant 3 is there for, to give us these very difficult questions. Okay, that's what variant 3 is there for. Okay. Um. Okay. Moving on. Moving on to the previous question. Moving on to the previous question. Okay, this is question. Okay, starter motor. So we can escape. We can just ignore II now. Now we have a part of the relay. Okay, and we need to start this battery. Actually, we can just ignore this question now. Okay, that's yes. Let's start it from here. Okay, let's start the question from here and then move back to the remainder of this question. Yes. Okay. Switch S, okay, we have a relay consisting of what? A plastic case, okay, plastic case, two flexible springy strips X and Y, which are made of soft iron. X and Y are made of soft iron. These iron strips act as a switch, okay, connected between terminals W and Z. We have terminals W and Z. Figure 7.2 shows the equipment inside the magnetizing coil. Inside a magnetizing coil in figure 7.2. Magnetizing coil is in series with the 12 volts battery. Okay, switch S is now closed. Explain what happens to the springy iron strips X and Y. What happens to these strips X and Y? Basically, if you think about it, you have a coil, which is attached to a battery. This battery will create a current, and this current will create a magnetic field. So it would create a magnetic field. So we can say that X and Y are both magnetized. They are both a X and Y are both magnetized. صح? They are both magnetized. When they are magnetized, what happens? Okay, they have, okay, X and Y both have opposite ends. Why do they have opposite ends? Because well, basically you can say one part is North Pole, and the other part is the South Pole. For example, if we say that the W is the North Pole and this part is South Pole, then this is a South Pole and this would be a North Pole. So these ends will touch. Why? Because they are attracted. Okay, so the ends, okay, X and Y, okay, X and Y are attracted. Why? Because they have opposite poles. Because they have opposite poles. That's it. That's it. So they touch. Will they touch? Yes, they will touch, completing the circuit. Okay. Okay. They eventually touch. Why? Because they are attracted. Okay. And we will complete the circuit. Next part of the question, we will draw the circuit. The power of the starter motor is 1.8 kilowatts, which is operated by this battery. Can I find the current? Yes, you have power and you have voltage, which is 12 volts. Can I find the current? I equals P over V. So basically, the power is 1,800 watts divided by the voltage, which is 12 volts. You have the current 150 amperes, which is a huge current, which is very true in the car batteries. Car batteries have very, very high currents. They are extremely dangerous. Car batteries are extremely dangerous. 150 amperes. The starter motor is now connected between terminals W and Z. Explain why the copper wires with large cross-sectional areas are used for this circuit. Again, I just said it. You have a very high current. You have a very, very high current. Why would I use a much thicker wire? As you increase the thickness, as you increase the diameter, what happens to the resistance? As you increase the diameter, the resistance decreases. Okay, the resistance decreases to allow, okay, which allows for a large current to pass. So as the area increases, the resistance decreases, allowing a large current to pass. You can also talk about the energy losses. Okay, in this question, as you decrease the resistance, what happens to the energy lost? Energy lost also decreases. Okay, energy lost decreases. Okay. Figure 7.3 shows the relay and the symbols for the car battery and the starter motor. Springy iron strips X and Y act as the switch. Can I complete the circuit? Yes, I can complete the circuit. Yes, I can complete the circuit. First of all, first of all, you need to connect the motor. You need to connect the motor. How can I connect the motor? Basically, the motor will be connected from this end to the battery. From this end to the battery. And from this end to the starter motor. Okay? From this end to the starter motor. Is this circuit complete? No, it's not complete yet. Why? Because point W needs to be also connected to the circuit. Point W needs to also be connected to the circuit. So if you think about it, oh, this is a complete circuit now. This is a complete circuit now. Why? Because you have the current that would pass through the coil. Okay, the current would pass through the coil, and the current would pass, creating a magnetic field, and thus the magnetic field will be opposite magnetic fields would attract in this coil, or in this uh, springy ends. Okay, X and Y will now be attracted. Okay, X and Y will be attracted. Okay, let's solve another question. Okay, let's solve another question. um, hmm, these are quite, I need okay, we can solve this question. Okay, it's not that hard, I think. Question, page 347. Page 347. Can I solve it? Yes, definitely we can solve the question. As we have this magnet which is moving, okay, it will move downwards. Magnet is fixed to a small trolley. The trolley is released from point A as it runs through the coil from right to left. State and explain what is observed on the galvanometer. What's observed on the galvanometer? As the magnet moves through the coil, as the magnet moves through the coil, what happens? What happens is that the magnetic field lines cut the coil. Magnetic field lines cut the coil, inducing a current. Okay, inducing a current in the coil, causing the galvanometer to deflect. Okay, as the magnetic field lines. Okay, magnetic field lines cut the coil, producing an induced hmm, an induced an induced current in the coil, in the coil, and then we can say the galvanometer deflects. Galvanometer deflects, meaning that the galvanometer will move either to the left or to the right. It will then return back to zero. Why? Because the magnet will move away. The magnetic field will no longer affect this coil. The trolley is now released from point B. State what is observed by the galvanometer and whether it's different or not. Okay, as it moves from point B, at point B, it's at a much higher point, which means that the speed of the trolley as it passes through the coil would be much faster. So the deflection will be much greater. So the galvanometer, okay, galvanometer has a higher or a larger deflection, a larger deflection. Why? Because the speed of the magnet or the coil or the speed of the magnet or the trolley, okay, is much faster. Okay, because of the speed. Okay, I need to find, yes, this is a better question. A much better question. I like this question. Question, yeah, this is page 345. Describe how the direct current DC differs from an alternating current. DC, how does it differ from an AC current? Basically, the current moves in only one direction. DC moves in only one direction, while the AC moves in two directions. Moves back and forth, okay? Moves back and forth. Figure 9.1 shows how the voltage output of an AC generator varies with time, starting from a voltage of 7.2. This is the maximum voltage, 7.2, and the minimum voltage is also negative 7.2. Negative 7.2. So this is an alternating voltage, which also has an alternating current. The heater is connected directly to the AC generator. It has a current of 0.75 amperes. 0.75 amperes. Can I draw or can I sketch the graph to indicate how how the current varies with time? Yes, definitely I can do that. Let's zoom in a bit. The maximum current, the maximum voltage was at zero. The minimum voltage was at negative at 0.2. The maximum voltage in the opposite direction was at 0.4, and then 0.6, and then 0.8, and then 1, and then 1.2. So can I plot the points? Yes. The maximum current would be 0.75. So at this point I'll have a small x. Okay, whatever. At the minimum would be at 0.2. The maximum in the opposite direction would be at 0.4, which is negative 0.575. Okay, and then 0.6, and then 0.8, and then 1.0, and then last but not least, negative 0.75 at 1.2. Can I draw the curve? Yes, I can draw it. It's a sine wave or a cosine wave. Okay, cosine wave definitely, because it starts from the maximum. Okay, moving in this direction. So this is a cosine wave. Okay, this is how the final wave would look like. Hmm. Calculate the power produced by the heater when the current is 0.75. Can I find the power? Definitely power equals VI. Power equals VI. So you have the voltage, which was 7.2, times the current, which was 0.75. 7.2 times 0.75 will give you a power of 5.4 watts. 5.4 watts. Now we have a generator and we have the coil in this horizontal position. This is a horizontal position. On figure 9.1, draw a straight arrow to indicate the direction in which side AB of the coil is moving. In which side AB of this coil is moving. If the direction of rotation is in this direction, it's quite easy. You don't need to use Fleming's left hand rule or right hand rule or whatever. If it's moving in a clockwise motion, then this part of the coil AB will be moving upwards. It would be moving upwards. Definitely CD would be moving downwards. Deduce the direction of the current induced in AB. Direction of the current induced. Induced. When he says induced, induced, created, generated, generated. So I will use the Fleming's right hand rule. Fleming's, right hand rule. Can I use Fleming's right hand rule? Definitely I can use Fleming's right hand rule. North pole to the south pole. So, north pole. Index finger is pointing towards the right, and the force is moving upwards. And the thumb is moving upwards. Therefore, the middle finger would be kind of into the page. Into the page, or from A to B. Okay? From A to B. Oh. So direction would be into the page, from A to B. Why? Because the magnetic field lines, okay? Magnetic field from north to south, from north to south, the force is upwards. Force is upwards. We can say that the current would be into the page or from A to B due to Fleming's right hand rule. Due to Fleming's right hand rule. Okay. Hmm. The rate at which the coil of the AC generator rotates increases. The speed increases. State two ways in which the alternating voltage changes. How does this alternating voltage change? If you speed up rotation is much faster. How will the alternating current, alternating voltage, how will it change? Definitely, the output voltage, the minimum and maximum voltage would increase. So instead of it being 7.2, it would be much higher. So, okay, it would have a greater voltage, it would have a greater voltage. It would also have a higher frequency. Why? Because the speed has increased. You're creating more waves in a shorter amount of time. More waves in a shorter amount of time. So the frequency increases as well. The frequency also increases. Frequency increases. Okay. Yep. Let's solve another question. Okay, we can solve this question quite quickly. Suggest a metal from which the magnetic material is. It's usually steel. This is from steel. The magnet is moved towards the left. It's moved towards the left, so it's moving in this direction. Yeah, we just said it. Okay. The galvanometer deflects briefly and shows that there is a current in the coil. As the magnet um, as the galvanometer deflects. Explain why there is a current in the coil. Explain why the current is there in the coil. Because of the cutting of the magnetic field. So basically, we'll say that the magnetic field lines of the magnet cut. You have to say cut. They have to cut the coil cut the coil, producing or inducing an uh, producing an induced current, an induced EMF, induced current or EMF in the coil. Okay, producing an induced EMF in in the coil. As the magnet is moving near the coil, as it's moving near the coil, and Q behaves as a magnetic pole. State the polarity of the end Q and explain why it has this polarity. Why does it have this polarity? Again, as the magnet is moving towards it, would it repel or attract? It would repel. Why would it repel? Okay, why would it repel? Because it opposes the motion or opposes the force acting on it. Okay, opposes the magnet, the force acting. So, and Q would repel, meaning that it has to be a north pole, and Q has to be a north pole. Why is it a north pole? Because it opposes yeah, opposes the force acting on it. Force acting on it. Suggest two ways in which the deflection of the galvanometer can be reversed. How can I reverse the deflection of this galvanometer? For example, if it was deflecting to the left or to the right. Okay, how can I reverse it? By either reversing the polarity of the reversing the poles of the magnet, or by reversing the direction of the motion. So instead of it moving to the left, it should move to the right, and you will have a current in the opposite direction. It will deflect in the opposite direction. Okay, not bad. I know, we're solving a lot of questions, but honestly, for this lesson, okay, you need to solve a lot. Okay, this is the most important lesson in which you need to solve. You need to solve probably all of the questions. Okay, but I'm trying to pick some of the more important or the more difficult questions. Okay, I'm trying to pick out the more difficult questions. Using the axes. Okay, you have a coil which is in the horizontal position. it's in the horizontal position. Using the axes in 9.1, sketch a graph to show how the voltage output of the generator varies with time during a period of 0.04 seconds. He says that the coil completes one rotation every 0.02 seconds. Every 0.02 seconds. Can I draw the curve? Can I draw the output? Yes, I can draw the output. Question is, on this output voltage, I will draw two waves, two complete waves, two complete waves. One of them will complete the rotation between 0 and 0.02, and the other one will complete another full rotation between 0.02 and 0.04. At this position, at this instant, at this instant, should the starting voltage be the maximum or should it be the minimum? What do I mean? Should it start from zero or should it start from a number much higher than zero? Let's think about it, okay? At this position, it should definitely start from the maximum output voltage. Why should it start from the maximum output voltage? Because we call this position the horizontal position. The horizontal position, okay? The horizontal position at this instant it will start to move. Okay, this is an anti-clockwise motion, so this part will move upwards and this part will move downwards. At this instant it's cutting the coils at 90 degrees, which is the maximum output voltage. The maximum output voltage happens at when you have a 90 degrees cutting or a perpendicular cutting. At this instant, horizontal position, when it's cutting the magnetic field at what? At 90 degrees. Okay, would it be wrong for this question? For this question, would it be wrong if I start from zero? It wouldn't be wrong. But so I'm telling you, the more accurate representation of this output voltage would be to start from the maximum position. Would be to start from the maximum position. Why? Because at this instant, the coil is at the horizontal position. It's at the horizontal position. So at this point, it would start from the maximum, okay, moving to the minimum, okay, and then to the yeah, the maximum in the opposite direction, which is it should be at 0.01, okay, 0.01, and then moving back to, okay, the maximum at 0.02, maximum at 0.02, and then I will complete another cosine wave, complete another cosine wave, okay, and then ending at the maximum position at 0.04. Okay, horizontal position means the maximum output voltage. Horizontal position, maximum output voltage. Okay, okay, good, not bad. Vertical position would be the minimum. Vertical position would be the minimum. I need to solve one or two questions regarding the DC motors. So let's move on quickly to the DC motors, and then that would be it for today. Okay, so moving on to DC motors. Okay, this is again, this is called the horizontal position. So at this position, at this instant, you'd have the maximum output. At this position, you'd have the maximum output. Okay. Yeah, moving on again, horizontal position, maximum output, horizontal position, maximum output. Okay, yeah, moving on quite quickly to the DC motors. Okay, most of the questions are in the horizontal position. I have no idea why. Okay, yeah, DC motors, page, let's say page 319. Okay, page 319. Okay, hello. We have a DC motor. He said that you have a DC motor and then explain direction of the turning effect as seen by an observer at O. In which direction will it rotate? We need to use Fleming's left hand rule. Fleming's left hand rule. Okay, so the direction of the force. Okay, the force on each of these on the left hand side, on the right hand side. Can I find the force on the left hand side and on the right hand side? Yes, definitely I can find the force on the left hand side. And this is the current, it's moving in this direction, and the current is moving away in this direction. Then the magnetic field is from the north to the south. So using Fleming's left hand rule, I'd find that the index finger is pointing towards the left and the current is moving inwards or into the page on the left part. current is moving into the page on the left part. First finger, which is the index finger, is moving to the left. Middle finger is moving into the page. So the force, which is the thumb, moving upwards. Therefore, the force on the other part of the coil would be moving downwards, indicating that this is a clockwise rotation. This is a clockwise rotation. Why? Because the force on the left hand side is upwards. The force on the left hand side is upwards, while the force on the right hand side is downwards. Force on the right hand side is downwards. Okay? The coil is replaced by an otherwise new coil with three turns. State how the turning effect compares with the turning effect in AI. If you increase the number of turns, what happens to the rotation? It definitely increases. Okay, the rotation, the speed increases. Okay, speed increases. A third coil is identical except that resistance is 3 times greater. The potential difference across the coil is the same as the potential difference. State how the turning effect compares with the turning effect in I. As you increase the resistance, what happens to the current? What happens to current? Current decreases. So when the current decreases, what happens to the rotation? It's much slower. Okay, turning effect. Okay, it's much slower, so it decreases. Why? Because the current decreases. Okay. Okay. Hmm. Okay. Question 10. This would be the last question for today. Describe and explain the movement of wire AB when there is a large current from A to B. Large current from A to B. From A to B. As the current moves from A to B in this. Um, oh, actually, let's ignore this question for now. I need to solve another question, another more important question. Yes, this was okay. This was a more important question for now. State the polarity of poles A and B. Poles A and B. If the south pole is attracted or is looking to the left, therefore this is a north pole and this is a south pole. So A is north and B is south. A is north and B is south. You have a wire, current carrying wire in a magnetic field. Draw an arrow to show the force on this wire. The arrow showing the force on this wire would definitely be upwards. Why? Because the index finger is from north pole to south pole. The current is moving kind of to the right. Therefore, the force would be upwards. The force would be upwards. This would be the force. The easiest 2 marks you'd ever have. Easiest 2 marks you would ever have. So the force would be upwards. Okay. طيب. That's it for today يا شباب.